Hey everybody, Dr. J for CCJ 3701 Research Methods in Criminology. Back to bivariate stats, crosstab, and chi-square. This is part 2 of the lecture. We kind of wrapped up doing an actual crosstab example. So just to back up, right here we had two variables, a bivariate test where we had one variable that was a nominal variable that just had categories of reasons you go to the doctor, and that's here in these rows. That's our dependent variable, our outcome, why you would go to the doctor. And then over here, we had another nominal variable, which is called gender, male, female, on your gender that we think is predicting why people go to the doctor. So that's our independent variable. So remember, in a crosstab, you usually put the independent variable in the column, and you usually put the dependent variable in the row. You don't have to, per se. That's just kind of common practice. Some people like it to display and format differently depending on where they put each variable. So ultimately, it really doesn't matter. The information in the cells is going to be the same, but that's just what people usually do. So again, we're going to run our little chi-square statistic with our cross tabulation of all the answers across one variable with the answers across another variable and see if we actually get anything statistical out of there that would be true. So otherwise, this is all cute and everything, but do we know if gender really does matter, why people go to the doctor? So that's why we have to run a chi-square statistic to tell us, are these differences real? Can I use category membership over here, gender, to predict category membership over here, reason I go to the doctor? Or is it just chance and something we find in the data that's kind of a circumstance? So that's why we run the test. In SPSS, you get this little box underneath your crosstab. It's called a chi-square test. And you see there's a lot of pieces of information here, but we don't use all of it. We just use a few pieces. So I'll walk you through the important stuff. The rest of it is really just mathematical products from the equation that SPSS ran, so you don't have to concern yourself too much with it. But the first thing people do is their eyes go to the very right box, which is over here, and I put this little arrow right here so you can see. So it said asymp sig two-sided. That's basically asymmetrical significance two-sided. That means that's our statistical significance, or our p-value. Okay, we're going to talk about p-values in a moment. So that is some meaningful information that we can check. We also have this little df in the middle, and it says 6. Okay, that is degrees of freedom. Okay, we use a lot of abbreviations in stats. And then down here it says n of valid cases. In this case, it told us we were running data across 380 patients that answered both the gender question and the reason I go to the doctor question. So some people have noticed, hey, how come the number of people in the data set tends to shrink when I start running statistics? Like, maybe I had 500 patients, but then when I ran this crosstab test, I only have 380. Why is that? Where'd those other people go? And I say, well, some of them may not have provided data on one of those questions, so you can only analyze valid responses. If they didn't answer that question, then they're not going to get included in the statistic. Maybe they only answered the gender question, but not the reason they went to the doctor question. So they're not going to get pulled in there. So you're not going to have all the information for everybody. You'll notice this, the more you require of your variables and your data, the fewer cases you have to analyze, because that means you're asking for more and more information that came from your respondents, okay? And sometimes the information is a little sensitive and people don't want to give it out. So just keep that in mind, that your cases start to shrink down the more demanding you get on things you wanted them to provide you. Okay, so let's talk about the pieces inside this little piece of output in SPSS. So chi-square outputs from SPSS generate degrees of freedom and statistical significance. We're going to talk about those two things briefly so you know what they are. Generally speaking, degrees of freedom, they're kind of just nice to know pieces of information. We don't use them a whole lot unless we're trying to troubleshoot or understand more of what we have to work with. So I call this the choosing your team analogy. Imagine you're picking people to play on a team. You have 11 positions to fill and you have 11 people to put in those positions. So how many decisions do you have to make? Well, in fact, you only have 10 decisions, because when you come to the 11th person, there's only one spot left, one position, so you don't really have a choice. They have to go there. So you actually have 10 degrees of freedom, as it is called. So how much can I move people around, until I only, have one limited choice left? So likewise, when you have a sample, the degrees of freedom to allocate people in the sample to a test is always going to be one less than the total number of people you have. So if you have if you have 11 people in a sample, then you have degrees of freedom as n minus 1. n meaning 11, so you only have 10 decisions to make. So that's kind of a quick way to understand degrees of freedom. But in statistics, it's basically the number of values in the final calculation of a statistic that are free to move, free to vary, independent pieces of information available to estimate other information. So it lets you know how much freedom you have. And we also have things like population parameters that we use. We're not going to get into that for now, but it's here if you want to look at it. But that's one piece of information that we use. Let's go back to this little 0.383 up here. What the heck is that? Well, that's statistical significance. Okay, so this slide is really important. You might want to take some notes on it because it's going to help you with your interpretation later. Because you're going to see this all the time. Significance levels come up in almost every statistic we run when you have 2 or more. Okay, so you want to get good at understanding how this works. So you see these in little journal articles, especially underneath tables where you see the results table. So it says significance at the p is less than 0.001 level, p is less than 0.01, p is less than 0.05. And then it has these little asterisks, 3, 2, or 1 little stars next to it that start to show you at what level something's significant at. So what does that all mean? Oh, I would pay so much money back when I was an undergraduate if somebody would have just explained it to me in layman's terms, but basically this is what it is. So significance levels, we call them p levels. I also call them probability levels. How likely a result is due to chance. So is this actually really true, or is this just circumstance? Okay. The most common level is used to mean that something is good enough to be believed is 0.95, or meaning that it has a 95% chance of being true. Okay. However, this value is also a little misleading. No statistical package, SPSS, Stata, Excel, R, any of those big statistical packages out there are ever going to spit out a 0.95 or a 95% to indicate that. Instead, it will show you a 0.05, meaning that the finding has a 5% chance of not being true, or essentially being false, which is the converse of the 95% chance being true. So instead of showing us how likely it is to be true, it shows us how likely it is to be false. Okay, so to find the significance level, just subtract the number that you get in SPSS from 1, and it shows you, what chances it is of being false or not being true. So if you have a value of 0.01, it means there's a 99% chance that it's true and a less than 1% chance of it being false. So in statistics land, we love small numbers because that means that our result has a very low chance of being false, that we can count on it to be true. This is probably true. Even if we did it again and again and again, and more studies, more samples, more data, we'd still continue to find this particular association or relationship or whatever. So we like significance levels, but that's essentially significance levels in a nutshell. So in English, this is how to write about it in the substantive way. Significant means important, but in statistics it's not necessarily that way. It means very probably true, or not due to chance. So a research finding may be true without being important. When statisticians say a result is highly significant, they mean it is very probably true. They do not necessarily mean it's highly important. In the real world, if something has a 90% chance or more of being true, a probability of less than 0.1, it really can't be considered proven, but it is probably better to act as if it were true rather than false. So in the world of criminology and working with human beings, we want to feel ethically good about our results that are messing with their lives, right? So we better be pretty darn sure that this result is true before we use it to further implicate their lives. Okay, so we have a very high standard of being less than 5% false, or being 95% true, or 99% true, or even more, okay, before we accept it as a scientific truth. And again, human beings, very high standard, because the consequences would be horrendous. If it was probably true, but we're not really sure, we're not going to make changes to people's lives based on being probably true. That's just unethical, unfair, not good science. We hold that high standard for a reason. Okay? This is just another way of thinking about a significance level. If you do a large number of tests, maybe in multiple data sets, multiple surveys, and you have the same kinds of questions over and over and over again, falsely significant results are a problem. Okay? So a 95% chance of something being true means there's a 5% chance of it being false. So out of every 100 tests, that show results significant at that 95% level, the odds are that maybe 5 of them would do so in a false manner. Okay, so we still feel pretty confident, pretty good about it being true. The best way to approach this possibility from a statistical point of view is to repeat the study, and that's where you hear the word replication, and see if you get the same results. If something is statistically significant in 2 separate studies, it's probably true. Okay, in real life, it's not always practical to repeat a survey. And there's some other techniques you can do to kind of retest things. We're not going to get into that, but there are other ways you can try to do it. So let's go back to our example. We got a 0.383. So what does that actually mean? That's actually kind of a big number. It's not that little 0.05, 0.01, or 0.001. Okay, we like tiny numbers, not large ones. So again, think of this as a percentile. That means this has, if we subtract the 0.383 from 1, okay, that means this has a 62% chance of being true and a 38% chance of it not being true or being false. Okay, so basically we can't accept that. It doesn't meet our burden or our standard of being 95 or 99% sure. And so when we get a significance level that's a number that looks like this, then we basically say, okay, we can't prove that there really is a true relationship or a true association going on here because there's too much room for uncertainty. Okay, so we basically reject it and we say, I accept the null, that there really isn't an association between patients going to the doctor and their gender. I don't have enough evidence to feel certain or feel good about it being true. Okay, but that's basically it. That's the chi-square test. That's how it works. It's pretty simple. Again, you're just predicting category membership over here to category membership over here, and that's it. So it's kind of fun. You can do lots of different tests with it. You can get strangely creative in some of the data sets you have, and you can try things. But remember, if you're going to kind of play in the data and try some tests, you have to follow the requirements of the test, which means you have to use nominal variables or ordinal variables. You have to use categories, okay? Doesn't work particularly well with interval ones, although some people treat the number as though it's a category, and you kind of can if you want to. But most of the time people are using tests with data that has little category attributes to it. Okay? So hopefully you find this helpful, and we'll see you in the next lecture.